Hello friends. Today, let's understand natural oscillation and how it works in electrical circuits. To demonstrate this, we need the following components. A 6V battery, a resistor, a push button, a capacitor, an inductor. Understanding the process: when we press the push button, the capacitor starts charging through the resistor from the 6V battery. When we release the push button, the circuit changes. Now, the capacitor starts discharging through the inductor. This discharge creates an oscillating current because of the interaction between the capacitor and the inductor. This type of oscillation is called natural oscillation, as it happens without any external force once the circuit is set in motion. What determines the frequency of natural oscillation? The oscillation frequency, known as the resonant frequency, is determined by two factors: the capacitance C of the capacitor, the inductance L of the inductor. Mathematically, the resonant frequency depends on both these values. A larger capacitor or inductor results in a lower frequency oscillation, while a smaller capacitor or inductor results in a higher frequency oscillation. What happens when resistance is present? In a real-world circuit, we usually have a small amount of resistance present due to wires and components. This causes energy loss in the form of heat, which affects the oscillation. If the resistance is small, the oscillation continues for a long time, but the amplitude, strength of oscillation gradually decreases. This is called damped oscillation. If the resistance is high, the oscillation fades away quickly. The system loses energy faster, and the oscillations stop sooner. If the resistance is too large, the system might not oscillate at all. Instead, it will slowly return to its original state without completing multiple cycles. Types of damping in natural oscillation: light damping. The oscillation continues for a longer time, but the amplitude slowly decreases. Critical damping. The system returns to its equilibrium as fast as possible without oscillating. Heavy damping, overdamping. The system takes a long time to return to equilibrium without oscillating at all. Practical applications of natural oscillation: radio circuits use LC circuits, inductor plus capacitor, to generate signals at specific frequencies. Quartz watches use mechanical oscillations to keep precise time. Power circuits use oscillators to regulate voltage and signals. Mechanical systems such as bridges and buildings also experience natural oscillations, which engineers must consider while designing. Natural oscillations are everywhere, from electronic circuits to mechanical systems and even sound waves. In our next session, we can discuss how to visually simulate this effect and analyze different damping conditions. Thank you for listening.